computer. Okay, right. So what, do you have a specific question or do you want to kind of go through it?
Probably go through it. That
Okay.
would be great.
So for gamma decay, gamma is the emission of a photon from an excited nuclear state. And so when a parent decays to a progeny, in this case, this is for americium-241, decays by alpha, goes to this neptunium-237 data here. And, and it doesn't go to this excited state all the time. Sometimes it goes to that excited state. And then there's a percentage of the time where it's at that excited state and it de-excites by emission of a photon.
Correct, correct.
Okay, so so if I have a sample of americium-241, I can put it on a gamma detector, and I should be able to, based upon sample geometry, the detector efficiency, and all this, I should be able to calculate how many counts I'll see. So let's go through some of the data here. The gamma energy is 59 keV, reading it from here, and it's the detector sees 15.5% of the photons. In other words, at that energy, the way the interaction of the photon with matter, only 15.5% of the photons are even going to be seen by the detector. Okay, so we got to take that into consideration. So, and then when the americium decays, 35.9% of the time, this is really weird because it's 3.59 times 10 to the 6th times 1 times 10 to the minus 5. That's where I get the 39.5% from, okay? So if I know I have 75 micromole of americium-241. So my question is, well, how many gammas am I going to see? And we know from this fundamental equation that the activity, the number of decays, this equation here, is equal to the decay constant times the number of atoms. So the decay constant is log 2 divided by the half-life. We turn the half-life into seconds. Log 2 divided by 1.37 times 10 to the 10th is 5.08 times 10 to the minus 11 seconds to the minus 1. That's our decay constant. And it's the number of atoms. Well, if I tell you that there's a micromole of americium-241, or excuse me, 75 micromole, well, 75 times 10 to the minus 6 moles times 6.02 times 10 to the minus 23rd atoms per mole, that gives me how many atoms there are. Okay, so I've got these two parts of the equation. So I can get what the activity is. But for the detection, remember, we said 15% of the time, you'll see the gamma. And from this decay, only 35.9% of the time is that photon even visible. So we got to take this number and multiply it by the photon yield, and then multiply it by how good that detector is for seeing that photon energy. And detectors, depending on, they vary with how well they see the photon in terms of energy. High energy stuff goes through matter pretty effectively, doesn't have a lot of interaction. There's a peak around 150 MeV for this material, excuse me, 150 keV for this material, where you get a lot of, say, a higher efficiency.
Okay. I think I'm kind of, I was confused on that efficiency because I was thinking that efficiency is from the decay, and I just realized, oh, it's the detector's efficiency.
Right,
so
yeah.
I'm wondering, why do you, at the end, you multiply the 15%, and then again multiply by another percentage, you know?
So you think about it, like if I give you something in moles, in how many moles, you can calculate the number of atoms. Well, activity times lambda n gives me the activity is equal to lambda n. That's the number of decays per second. And of those decays, 35.9% of them result in a photon, and only 15.5% of those photons are seen. So that's where those numbers come from.
Got it.
Yeah.
Okay.
Yeah, this would be something that'd be much easier if we had a lab, like what I'm doing right now. Like that's why I was a little late. I was changing a gamma sample.
Mm, cool. Okay.
All right.
Some notes. Someone can ask.
Any Allison, do you have a question?
Sorry, I have 3 monitors going and it's hard to get my mouse on the right screen to unmute. I'm just here to lurk and listen for now. But I'll ask if I have anything.
That's acceptable. And I am recording this. So
Great.
You know.
Oh, thanks.
Yeah. So Yongyan, do you have another question? You can monopolize the time. Allison yielded the floor to you. That's what all these impeachments have taught us, the Robert's Rule of Orders.
Okay. Then maybe my next question. It's not really from the lecture, but so I recall that when I was doing the lecture 3 quiz, there was one. I cannot recall exactly, but I think it's something that I was given activity, and then I was supposed to calculate the counts. And I remember at the beginning that I was trying hard to find the relationship or in terms of the formula, how they relates between activity and counts. And then I think I went a really complicated way to get the answer. But then when I see the answer, oh, it's just multiply the rate, or was it like percentage? Multiply the percentage by the activity, and then I get a count.
Yeah, so it's basically this question.
Yeah, I got
right.
a little.
Right. Yeah, it's this question. It's the one we just went over. But I made it kind of simple. You have 100 becquerel. The detector sees 2.5% of those, whatever the decay is. And then if you count the sample for 90 seconds, I think it's 225 counts. Right? Mm-hmm. And then the follow-up question is, what's the error? Well, it's the square root, so it's 15. So it's 225 plus or minus 15 counts. So if you put that sample on within one standard deviation, you would expect the counts to be 225 plus or minus 15 counts.
That would make sense. Yeah. That would make sense intuitively. But I was thinking, when I was doing that problem at first, I was using the formula, what was it? A equals lambda times E.
Right.
And I was trying hard to find out what's the mole. And then I can use mole to find out count. I don't know what was I doing, but I went.
No, I get that. A lot of times you're given an equation like, okay, let me use everything's. I have a hammer and everything's a nail, right? So, and I tried to make this a little bit simpler, but I could have said, oh, there's so much, so many grams of a material that has this half-life. Then you could have calculated the activity and then gone from here, just like in the example that we went over.
Got it. Yeah. I think that's my main conclusion.
Okay. Excellent. Okay. And was there anything else in lecture 3?
I think that will be it.
Okay. And anything in lecture 4?
Yeah. Would you talk about a little bit more about the hindrance factors?
Okay. So let me pull that up for
maybe because I know we can find the factors from the table of the isotopes, but then I was because that document is really, really long, and I don't really know anything I want.
And generally speaking, what I'll do is say on an exam, I would actually put the data available. Like I would put the section of the table of the isotopes.
Oh, that would be great.
Yeah, I understand it. I don't want to test you in how well you can recall information. Okay, so what the hindrance factor basically says, it's imagine you do some calculations and you say, oh, the half-life should be this value. And the way we predict the half-life is I say, well, there's an alpha particle that's in a well, right? It's in a nuclear potential, and it's going back and forth, right? It hits the barriers of that potential once every 10 to the minus 21 seconds.
Mm-hmm.
So in a second, it's hitting it, 10 to the 20 something, 10 to the 21st times around there. So it's really probing that barrier. Now we can make a calculation that says, okay, the half-life based upon the properties of that nucleus should be a certain value. And then we go on and measure that half-life because we can easily, we can measure the half-life. So now I compare the calculated half-life and the measured half-life. And what happens, I think there's maybe one or two nuclei where it's not true, but most every nuclei, the half-life, hindrance factors are between 1 and 3 times 10 to the 4th. So they're all larger than 1, which means the measured value tends to be longer than the calculated value. And the reason for that is that the calculated value, and you go to the model, there's certain assumptions. And the main assumption is that alpha particle that's getting away from the nucleus is there 100% of the time. Well, what if that alpha particle is only preformed 50% of the time?
Mm-hmm.
Right? So I need to add that factor, that hindrance factor, into my calculation. So I may get, okay, an idealized system, I may get a certain decay constant or half-life, but then when I measure it, the half-life's longer. Well, the model could say, well, the alpha particle isn't together all the time. And where you see it's particularly true are for, all these deviations, all these equations that we went through, they're particularly true for even nuclei. So even number of protons, even number of neutrons. The nucleons, the number of protons and neutrons can be paired up like electrons. So they're sitting in this nuclear well, paired up, pretty much looking like alpha particles, ready to do their thing. Okay, let's look at an odd A nucleus, right? Where I've got an odd number of protons and an even number of neutrons or vice versa. So one of those, the highest energy, let's say it's odd number of neutrons. The highest energy neutron is unpaired. So in order to make that alpha particle, the pairing of the neutrons below it in energy needs to break. One needs to go up and make a pair, and then that alpha particle needs to form. So what the hindrance factor tells me is, it's a way of saying, well, what's the probability of that occurring? So it gives you an idea of how often this preformed particle is sitting in the nucleus. And then the other thing that could have, that could have influence on the hindrance factor is the fact that this equation, I talk about the distance here to the tunneling, right? We talk about tunneling, it's going to tunnel through this part of the barrier. This is a distance. This assumes pretty much a spherical nucleus with a skin thickness. The density kind of drops off, right? But what if the nucleus isn't spherical? That can also make the hindrance factor larger. It could also influence it the other way too, because if the alpha particle goes, imagine as the nucleus being shaped like a sphere, it's shaped more like a pancake, right? So if it tries to go the long way of the pancake, that's a huge barrier. It'll never get out. But if it goes the short way of the pancake, it's a higher probability because that this barrier that it needs to penetrate is smaller, and the half-life would be smaller. So the structure of the nucleus has some influence on that. We're not going to talk about that. I think for us, it's just an understanding. It's kind of your first step to think about that the nucleus has structure. and they had neutrons and protons. When as a chemist, we think of the nucleus as a dot, and it's got neutrons and protons kind of mixed up. Well, it's actually got a little bit more intricacies and detail. And what's kind of interesting is just from these sort of simple observations, the half-life of the alpha decay, we can gain a little insight into what's the property of the nucleus. And that's something that I think would be interesting for you to walk away from the class with is, you understand, well, how do they understand that nuclei have structure? Oh, yeah, well, it comes from the fundamental measurements that are performed, things like half-life and the variations from what you expect and what you actually observe. Like, I don't expect you to utilize and memorize these equations as part of the class.
Okay.
Unless you want to. I mean, some people very much enjoy math. I think it's important. What I like to do with an equation is just this: take the equation apart and show you physically what does that equation talk about? What are the components of it? So if you see the variation, it's like, oh, there's a physical linkage from what's written down in that equation to what's actually happening in the nucleus. I mean, honestly, as far as we know, it's not that I've ever delved into the middle of a nucleus. It's just that we do experiments and we take our data and we kind of make sense out of it.
Mm-hmm. Yeah. Okay. Thank you.
My pleasure. I love talking about alpha decay. All right. Any other questions?
I'm good for now.
Okay. All right. Yeah, and you're more than welcome. I know that this is often hard for students to just leave. You're more than welcome to do that. If you're done and you don't want to hang out anymore, by all means. My job isn't to make you sit there. Okay. But I often find that in this sort of relationship, I've often done that to people. We'll be done. I'll say, well, I'm just going to sit here till the time of the meeting is done. Like, no, I'm not going to do that. You can go. Like I said, I got a gamma sample counting, so and
you never know. You never know when somebody's going to ask a really juicy question you didn't think of, though.
Exactly. No. But at the same time, right, you're more than welcome to, if you're done, you're more than welcome to enjoy the rest of your evening.
I had a few quick questions actually based on what we were talking about. Here it actually goes back to lecture 2.
Okay. All the way back to lecture 2. Hey, well, you're not even supposed to remember information from lecture 2 by now.
Anyway, but considering the structure of the nucleus and what we were talking about there, I just wanted to review quickly what we were considering. Based on what particle we choose to bombard, right? Whether we're considering an alpha particle or an electron, whether it's a moderate speed or a high speed. And we talked about, like spherical versus, like idealized sphere, whereas you might have something different if you have like that high speed electron or something like that. So I just wanted to review that real quickly.
Yeah, so if you think about it, the way you would do this experiment is I would take a foil, right? And then I would take an electron source, a particle source, and impinge it upon the foil. And then I would look for this scattering, right? And this scattering is going to give me this, from this equation, I can deduce the area of closest impact. And this is also why, for copper, if I have a copper nucleus, I get between 10 and 20 femtometers. For uranium, it's between 30 and 60. It also depends upon the energy of the particle, right? As long as the particle, if I'm hitting a nucleus with a charged particle, I'm really measuring the Coulombic field. If I have more energy, it can get closer before being scattered, right? Now, when it comes to shape of nuclei, it would be very difficult to perform this experiment and try to get the change in this lattice parameter as a function of the nuclear shape. And let's say the nuclear shape is football shape, right? American football. Think of soccer, you'd be like, well, it's spherical. So it's shaped like an American football or a rugby ball, right? Now, when I do this experiment, the nuclei are not aligned, right? The nuclei are going in all random directions. However, if I wanted a chance to use this experiment to see if I can get a difference in this distance as a function of the orientation of the target, how could I do that? You could do it. How about if I took I would need to have a nucleus that had a magnetic moment. I put it in a magnetic field and they all align. We do this as chemists, nuclear magnetic resonance, right? We say, oh, we start them up and we let them go. So you're already familiar with this technique. Now that would be a tough experiment to do. You might be able to, choose the right nucleus where you get large differences and choose the right particle that's sensitive. And it's got to have a spin and parity that'll align in the magnetic field. And then I gotta do all this within a magnetic field. Well, you really got to want to do this. It's kind of a tough experiment. Although I certainly think it's an interesting experiment. What we're going to learn, the way you actually determine something about nuclear shape, has to do with variations in the spin and parity. In other words, I can calculate a spin and parity. When we get to the shell model is based upon a spherical nucleus. So I'll calculate a spin and parity, and I can measure the spin and parity of the nucleus. If they don't match up, what's wrong? The model that we built our whole life on is wrong? No. The nucleus isn't spherical. The model's based upon a spherical nucleus. And have you guys taken inorganic chemistry? Okay. What this is like, have you reviewed Taname-Sagano diagrams? So I go from OH symmetry of a molecule, right? So I've got nice OH symmetry. What happens if I pull on I'm going to call this the z-axis. What if I pull on the z-axis? That symmetry is broken. It has a different shape. My molecular orbital theory, where I go, oh, it's T2GEG, that doesn't work anymore, right? So you could actually get something about the molecular symmetry by looking at the energy transitions. It's very similar with the nuclei. If a nucleus is supposed to be round, I can stretch it this way, or I can stretch it this way. They're going to have different shapes, and it's going to break that. It's going to change the way the orbital energies align, just like they do in inorganic chemistry. What we're very familiar with, or quasi familiar with, or we've heard of, the ligand field theory or something like that, right? Yeah. So, but it's basically rooted in the same math. So we're going to find out that if I take a nucleus and I align it, and then I look at the gamma decay, the angle of the gamma decay that comes out of the nucleus, I can get something about the shape, because the spin and parity, since it has a structure to it, it has a certain shape, it's going to drive the photon out, because spin and parity is electromagnetic and a photon is electromagnetic force. So that's, again, that's a lot of information. Not that it's going to, I don't know if it's going to show up on an exam. I don't think it'll show up on an exam, but it's bonus information. I'm giving you, additional information for your tuition money. It's bonus.
All right. I did have a quick note also while we're on this slide, right? So we do have this equation here where we have the D naught, and I wanted to note the relationship, or just make a comparison between that, and on the previous slide we also have a radius
right,
equation as well.
This R naught, yeah. I mean, the D naught you can almost think of as it's trying to simulate, kind of. The knot they're not particularly related, because this D naught is the closest approach. This is the closest approach from a head-on collision, and it's going to vary with the particle you use and the energy of that particle. This R naught is related to, you know, how nuclear density changes, the skin thickness. You know, there's a certain part of the nucleus which is super, super dense. And then a part that as you get towards the end, it's not as dense. The R naught is related to that density. So the less dense a nucleus is, the larger that R naught factor. Do you guys have any idea how dense a nucleus is?
Well, it contains most of the mass of an atom. Compared to an electron, I mean, it's like a little lead weight or something basically. And you had like compared to, I don't know what a good analogy would be, but it's pretty. If you put it on, I don't know what kind of surface, but it would probably fall through if you put it.
Oh, like if you had a cup of nuclear matter, just the nucleus, it would fall through the earth.
Yeah.
So we'll do it for an exam question. I'll ask you to calculate the density of a nucleus, and then I'll also ask you to look up the density of a neutron star, and you will see that they're similar. So, you know, but the only difference is, so imagine an object that has the same density as a nucleus, but it's kilometers in length. That's why it can form a black hole, right? It's just, and so, yeah, and as far as the percentage of the mass that's in a nucleus, an electron has a mass of half an MeV, 511 keV, so it's about half an MeV, where a nucleon, a proton or neutron, is 931, so it's about 1,000, right? So it's about a 2,000 to 1 ratio of the mass of a nucleon is 2,000 times more massive than the mass of an electron.
Now, in terms of, you know, density and things of that sort, I know we haven't mentioned explicit calculations so far in the lecture videos I've watched as of yet. Is that coming up in more detail, or is that just more of a conceptual thing?
Oh yeah, we're not going to go into, I mean, what I want within this class is that density varies. Again, it's giving you, it's trying to provide you with information on the details of the nucleus, right? And until you saw that lecture, you probably didn't think much about a nucleus. You didn't think that the density, you know, you probably go, well, it just drops off, right? Because as chemists, we like, there's the dot in the middle of the atom, right? That's all the nucleus does for you. So as far as the density is concerned, the change in density, we're going to pretty much leave it that, yes, it has variations in density. And yeah, there's specific nuclei. So for instance, there's light nuclei, which have a stable core, and then they have nucleon pairs going around them. They're called halos. And a lot of times it's easy to knock off those halos. Or deuterium, right? A hydrogen 2 with a proton and a neutron. Well, you can use the charge on the proton to almost carry that neutron and accelerate it into things. And then you break that and your neutron just keeps going. So you can almost think of it that the proton acts as a handle, but it's not an incredibly strong neutron-proton interaction.
Okay, all right. Also, I'm just going along this theme here of well, actually, so two related questions actually. The first is more of a basic question, but it goes along with what we're talking about. But when we're considering, you know, the binding energy per nucleon curve here, that classic, I don't even know if it's in this lecture. I think it's another one.
There we go.
Oh yeah, there it is. Yeah.
Yeah.
So, but yeah, when we're considering this classic graph we've seen many times, things like that. But just to sort of make sure that we have a good understanding of why we see such a dramatic increase there with the binding energy. Really, we can relate that to attractions, perhaps that, right, the increased rapidly attractive force between nucleons with each additional proton exceeds repulsions. An important point there, perhaps.
Mm-hmm. Yeah, and what it has to do, this is a way of also demonstrating where all these peaks are, wind up being close to magic numbers.
Yeah.
So
Okay.
it's the same thing when electrons fill shells, right? You get to a filled electron shell, and it doesn't want it. That electron, they're done. They don't want to interact anymore, right? Is that true? Can you make compounds out of noble gases?
Well, there are some exceptions, like xenon tetrafluoride, for example.
Very good. Very good. Yeah. Neil Bartlett did work with that. When I was in graduate school, he was also a professor. I got my doctorate at Berkeley, and he was also a professor there. So actually, a lot of people in the chemistry department at UW got their doctorate at Berkeley. Like Mike Heineke was a couple years ahead of me at Berkeley. He's now retired, right? So he's obviously a little bit older, but
yeah. He is having fun teaching the organometallics class this quarter.
Good. Are you taking that?
No, not the organometallics one. No.
Yeah, I was gonna say that sounds like a lot of fun, and I'm sure he would do an outstanding job of teaching that course. But yeah, so this relates to the energetics that are inherent in filling the shell, and it turns over. You get that maximum amount of iron. So it explains a few phenomena that are observed: fusion, fission, the stability, the fact that the iron group they're more prominent than they should be. Like if you drew a line, the relative abundance of an isotope and it's A, or an element and it's Z, it should be a straight line, but it's not. It varies off that. And there's an unfortunate consequence of that. Lithium, which is, something that's important if we want to go to, battery storage. Lithium is unfortunately off that line on the low end. It's less common than it should be because of some of these nuclear properties.
Wasn't it one of those elements that was originally produced early on in the solar system's history, but now it's just sort of declining away from here on out?
Well, yeah. And in fact, we will talk about, when we talk about nuclear reactions, we will spend some time on nucleosynthesis. So, because, as a chemist, I really think every chemist should be able to say, you're getting some, nickel chloride, nice colors. Where does the nickel come from? Well, it comes from Aldrich or Sigma, right? No. Where does that nickel, where is it made? Well, a chemist, in my opinion, should know that nickels are made, elements are made in stars, right? But they said the Big Bang, they were responsible for hydrogen, helium, and a little bit of lithium, and that's it. So if it was just that part of the periodic table, it would be boring. Yeah. In my opinion. I'm sure there's a lot of lithium, hydrogen, helium chemists that would disagree with me.
Yeah. Let's see. So I think, that clarifies that. But I think on continuing on with nuclear structure and things of that sort, when we're considering, the liquid drop model of the nucleus, what would you consider, to be above all the biggest limitation of the model? I mean, I think from my consideration, I was considering the fact that the nucleus, it has structure, it has shells. We haven't talked too much about shell model yet, but it's not just the liquid drop, it has that kind of structure which this model is somewhat lacking. But
yeah, and that's exactly right. It's this, I would say, from the what I think is very powerful about the liquid drop model. It's a pretty easy model in the sense, this model on the drop of water, something we're all familiar with. We understand how water behaves. And I would say the real weakness comes out in this delta term, where it's a pairing energy. It's a complete fix, right? I have to put in something that helps describe the even nuclei. So it's a fudge factor that goes in. And then when you look at this data, which shows the difference between experimental and liquid drop formula masses, there's areas where you're like, okay, that's not so bad. And then there's areas near the magic numbers like, yeah, that's a failure. If I want to understand something about 82 protons lead, it's not going to help me really get a good handle on the lead nucleus. But if I'm between shells, it's okay. It's a reasonable model. But that to me is, but it's a drawback, but it's also a way of, plotting the data like this tells you, there's something else going on in the nucleus, and that's what leads into the shell model.
Okay, so these magic numbers here, right? These particular, incidences of, abnormality really foreshadow what we're going to talk about with the shell model.
Precisely.
Right.
Yeah.
Okay, that covers that then. I did have, let's see. I guess we'll just keep going through the questions I lined up.
Yeah, Allison, you still content just listening in?
Yes, so far.
Okay, very good, very good. Yeah, please, do what's necessary. Yeah, okay, good. Yeah, the thumbs up, perfect.
Right, I did want to clarify in lecture 3, slide 18. Just there was some data on the left or the right-hand side. I just wanted to note to re-clarify on where we'll be able to acquire that ourselves if we were encountering such a problem.
Right. So, yeah, this was one of the first questions asked. This data, the detector efficiency, that is, every detector has a different efficiency. The way you acquire that data is I take a standard that has a number of different gamma energies. I know their activity, and then I go and measure their counts, right? So that tells me that at a given energy for this detector, what's the percentage of the counts that are seen. And by the way, as you can imagine, I can buy detectors that have really high efficiency. They're a little bit more money, as you can imagine. But the material germanium, so it has to do with how the germanium crystal is, how big that crystal is. And then some of the electronics can also have an influence on it. And then there's a possibility that I can put some additional components in my detector to suppress information. Let's say, I try to make a coordination where I only, if a detector, like I can take a detector and I can wrap another detector around it. If that other detector that's wrapped around it sees something, don't count that one that was seen before. And what's interesting about doing that is you have delays, and you can take a data point, delay it in time, so I can see if it correlates with another data coming from the detector. And if it says, oh, if I see this data point coming from this outside detector, which tells me the photon escaped, don't count that photon because it's an escape energy peak. It's not a real peak. We're not going to go into that, but I'm giving you an example. This detector, right, this detector efficiency is inherent for your detector system. And it also depends upon the sample that I use. If I have a sample that's, say, the size of a pin point, I have much better geometry than if I have something the size of a quarter, right? Because it's spread out, and the solid angle that the particles go out at can have less efficiency in interacting with the detector. And then the gamma branch, this is from data, this is an example of a gamma branch from the table of the isotopes. And what I'm going to show on the screen is I'm looking up my isotope browser. Hold on, I have to put on my glasses. Thank you. Okay. So, and I'm going to put in 241 americium. This is an app that I have. Right, this is from the IAEA, so you can download it. And then I go to americium 241, And it shows me, see if you can see the data.
Yeah.
Okay. And then what I'm going to look for is the gamma. Let me just see. Okay. See where it says gamma efficiency? It's 35.9%.
Hmm. Okay. Is that also available? I think the same people make that live chart of the nuclides as well.
I believe so. Yeah, but the live chart's also pretty good too. There's also a site in, on the web page, there's some links. Okay, so gamma data from Lund University. Table of the isotopes, Lund University. Here, I'll show you this data set. This is also a really good site. These people I knew when I was a graduate student. They must be old. So let's search for a nuclide. And let's look for 241 americium. Search. Okay, here's americium 241. Tells me the number of protons, number of neutrons, the decay mode, the half-life, the spin imparity, the percent abundance if it's natural. So I go here. And this is basically the same data that I just showed you. Here's the, here's the half-life, the neutron separation energy, the proton separation energy, how it's produced. This is the data that this is based on. This is the reference. And then I can go and look at here and say it's 59 keV, and it's 35.9%. Here's the percent. And then I can get things like the gamma levels and actually, let me go to the gamma levels. It'll do this. There's lots of extra data that you can pull out. Oh, it's waiting for the Berkeley site. Yeah, I'm not sure if the Berkeley site's still functioning. Yeah. Oh, the one site, sorry. So there are limitations in that. But this is also something, this is also something you can find online.
Okay, perfect. All right. Yeah, yeah, that covers that. Then I just wanted to note here, so when we have, when we were talking about half-life relationships and things like that in lecture 3, right, so when we have a non-equilibrium situation, I think I was comparing what we talked about. So if we look at slide 32 and 31.
In lecture 3?
Yeah.
Yeah, okay.
Yeah, I think.
These.
Yeah, so 32 and 30. Yeah, I think this is
33. Yeah, this is the numbering might, okay.
So maybe the numbering is slightly.
Yeah. But is this the figure you're interested in?
Actually, I think if we go back, let's see, it's entitled Half-Life Relationships, and it says, can simplify relative activities based on half-life.
Okay, right over here, right, yeah.
Yeah, so we do see, right, so with no equilibrium and things like that, so the daughter reaches a maximum activity when we have this equality here. And we also mentioned maximum activity of the daughter on the previous slide, I believe. Yes. And an equation was given for that there. Yes, and so I just wanted to note relationships there.
Yeah, and these, okay, this example is pulled for molybdenum 99, which decays to technetium 99M, which is a medical isotope. So if you separated the technetium from the molybdenum, this would tell you in about a day, it'll reach the maximum amount of technetium again. But the relationships, all the relationships are based, it's fundamentally solving a series of first order kinetics. So what's nice about nuclei compared to chemicals, they don't vary from first order. right? I can heat them up. I can freeze them. They don't care. I can put them under pressure. Couldn't care less.
All right. So then I guess going back to this slide here, right? So okay, so we do have that that relationship there. Once we have we have the decay of the parent, right? If it occurs super quickly, right, then
Right.
it might take a while for that daughter to especially has a comparatively longer half-life.
Right. And in fact, think about it as an extreme. What if the parent has a half-life of a second and the daughter has a half-life of 100 years? So in 10 seconds, all the parents gone, right? And now that daughter is just decaying away with a half-life of 100 years. So it's not at equilibrium. And when I say equilibrium, it's not the number of atoms, it's the decay rates.
Yeah. Okay. All right. Yeah, I think that covers that. When we were talking about modeling and things like that with that particular program that you showed us, I think.
Yeah, this one.
Yeah. So I think there was also a review question which stated, for example, if you were considering like a secular decay or something like that, I believe, where you could actually find the point in time. Yeah.
Like this one, right?
Yeah. You could actually find the point in time of where do we have that convergence.
Right. Now there's a general rule, and you say the equilibrium occurs in about 7 half-lives of the daughter, right? So in this case, this isotope, this thorium isotope, has an 8,000-year half-life. This radium isotope has a 15-day half-life. So you say 7 to 10, because if I'm at 3, if I do the calculation that 3,000 hours versus 4,000 hours, yeah, it's similar. They're not exactly the same, but you eventually reach a point where the decays are equal.
So yeah, there is some variation in that, but
right.
But 7 half-lives is kind of a rule of thumb. You're saying
exactly. I mean, some people say 10 half-lives, but 10 half-lives also. If I have something that's radioactive and I want it to disappear, you wait 10 half-lives and it's gone. Right. So if I have an isotope that's a half-life of, I contaminate my hood with fluorine 18, and I think fluorine 18 has a half-life of 22 hours. Come back, if it's really bad contamination, come back in 10 days, it's gone. The stuff that I use, the half-life, plutonium, 24,000 years, I can't do that. I have to be careful.
Yeah. All right. Well, I think that covers everything for now. If I run into something else, the next lecture is scheduled to be posted tomorrow.
Yeah.
I think on beta decay.
Correct.
All right. Okay.
I'm pretty sure I'm going to get there. Pretty sure.
Oh, will there be office hours posted for during? I think you mentioned it on the first lecture video that there'd be office hour opportunities during the exam period or something like that.
Yeah. So whenever I issue an exam, and what I'm going to do with the exam, I'm going to probably put it on the Canvas quiz. And I'll give you 2 chances, right? I'll post it, and it'll be due in 5 days. Then I'll post the answers, and then you can make any corrections you want. However, any changes you make, you should explain why you made those changes. So in other words, it's a way for people to look at the data, look at the questions and say, okay, I want to understand the material. Okay, I understand why this was a mistake. I missed an order of magnitude or something. And to me, the important thing is, making sure that people understand the information. So that's what I'm interested in. But between when the exam is posted and its due date, we will have office hours.
Okay. And it's a downloadable PDF document, so we can print it out and write on it.
Well, it'll. Right now, I'm thinking about putting it as a Canvas quiz. Would you prefer to have it as a PDF document or both?
I personally like the PDF documents, but I think it's just maybe for ease of writing and things like that. Plus, you don't have to be on the computer screen for that long of time.
Okay, all right. So maybe what I may do is print out a PDF, but you can always just input the answers into the Canvas.
That's true.
Okay, yeah, because what I like about the Canvas, the ease of grading is,
yeah.
I mean, I'm not going to lie to you. It's really nice to have it all spelled out and then to put in the reasoning behind the questions. You'll put in details on the answer. I look at it as a nice addition for a learning experience. But I completely understand that you would like to have the questions out. So I'll also post the questions as PDFs.
Okay, that's great. Perfect. All right. Thanks so much for your clarification. I do appreciate it.
I believe that's what I'm here for.
All right.
Okay. All right. If there's nothing else, I will stop the. Oh, you had another question?
Just continue on the discussion about the exam.
Okay.
So would that also mean that most of our questions will be multiple choice then? Because I was thinking exam should be like a little bit harder.
Yeah, so I would say that most of the questions are really going to be numerical.
Oh, okay.
Right. Yeah. Those and I mean some multiple choice. I will try to challenge you with the multiple choice.
Okay.
You know?
I was thinking would there be some partial credit somewhere?
Yeah. I mean it'll be there. Yeah. My exams are designed. How about this? When we go through the office hours before the exam, it's a good idea to just take an initial look at the exam. If there's any questions you have, you can bring them up at the office hours. Also, you can post them on the blog, right? Because if you post a question on the blog, that's like, that's similar to raising your hand in class. Everyone can see it. It's a matter of whether or not people will view it. But if you say, oh yeah, I'm doing question 2 and I want clarification on this point, I use this value. Is that correct? I very well may say, well, I would use this value and, whatever, and provide guidance towards that answer.
So the office hour session will be right at the beginning when the exam is released, or later on when we have a chance to look at it more?
It'll be, yeah, I think I'm going to release it either, let's see, the first one Friday or Saturday. And I probably will make it due. I may release it on Saturday and then have it due on Friday so that we'll have 2 office hours between it.
Yeah, that would be great. Yeah.
But as you said, having some time delay between when it's posted and when we discuss it is usually amenable to educational opportunities.
Yep. All right. Sounds
okay.
Good.
Sounds good. Thank you.
My pleasure. Okay. If there's nothing else, I will stop recording.